Hi friends, how are you today? I hope you are enjoying it. Then today we are discussing mass and abundance of nuclears. You already know that the mass and binding energy are interrelated. Uh, in this video we are going to learn about the mass spectrometer. The measurement of nuclear masses occupies an extremely important place in the development of nuclear physics. You can also take a note of that. Mass spectrometry was the first technique of high precision available to the experimenter. And since the mass of nucleus increases in a regular way with the addition of one proton or neutron, measuring masses permitted the entire scheme of stable isotopes to be mapped. Okay, നമുക്ക് സ്പെക്ട്രോമീറ്ററിനെ കുറിച്ച് നോക്കാം. Okay, all mass spectroscopes begin with an ion source which produces a beam of ionized atoms or molecules. For analyzing something we have to send some signal. Here we are sending a beam of ionized atoms or molecules. Often a vapor of the material under study is bombarded with electrons to produce the ions. In other cases, the ions can be formed as a result of a spark discharge between electrodes coated with the material. Ions emerging from the source have a broad range of velocities as might be expected for a thermal distribution, and of course many different masses might be included. Then first, for a mass spectrometer, the first material is the ion source. The next is the element is a velocity selector. Ion source, velocity selector, these are the parts of the first and second parts of the mass spectrometer. The velocity selector consisting of perpendicular electric and magnetic fields. The electric field would exert a force QE that would tend to divert the ions upward. You see the figure 3.13. Here you can see the figure 3.13. Yes, here. This is the ion source. This is the velocity selector. Okay. Then velocity selector. B field would exert a downward force QVB. Ions pass through undeflected if the forces cancel, for which here you can see that the force F is equal to QE electric force plus QV cross B. If the charges negative ions, Q becomes minus, right? Then force is zero. Then you can write QE. Okay, if force is equal to 0, you can write QE equal to QVB. QV cross VB sin theta, right? Theta 90. Then you can write QVB. Then now you can write QE equal to QV cross B. From that you can find the velocity is E by B. That is the velocity of the charged particle or the beam is depends on the electric field and magnetic field. You can control the velocity by controlling the electric and magnetic field. Then the final element is the momentum selector, which is essentially a uniform magnetic field that bends the beam into circular path with radius r determined. Okay, here you can see the schematic diagram of mass spectrograph. This portion may be asked in the final exam as an essay question. you please learn to write the block diagram, the schematic diagram, and you have to draw this in the essay. The mass spectrometer, the components are the ion source, the velocity, then momentum selector, then the beams will be hit on the photographic plate. The description is an ion source produces a beam with a thermal distribution of velocities. A velocity selector passes only those ions with a particular velocity, and momentum selection by a uniform magnetic field that permits identification of individual masses, so that we can only the selected masses will be detected only in the photographic plate. Okay, then we can see how it happens by the moment expression mv equal to qbr. How did we get this expression? For that we have to consider this image. You see that? Okay, a circular moving object, the instantaneous velocities at this position, the velocity is v1, at this position the velocity is v2. Then this is the center point, this is the radius distance, the both are r. Then the velocity, this point and this point makes an angle theta. If we draw this triangle here, this is a circular path. If theta is small, we can draw a straight line here. If theta is negligible, this curved path becomes a straight line. So we can draw a similar picture here, r theta. Then this becomes, this is the arc length. Okay, this the length becomes, if it has a constant velocity, then we can write this velocity is distance by time. So distance is velocity into delta t. So we can write this is v into delta t, this is r, this is theta. Okay, if we draw the velocity vectors, this v2, this v1, we have added that vectors v1 and v2. This makes a theta since it is similar as bringing this r into a perpendicular direction. Okay, so this both v1 and v2 makes the same angle theta. We both have the same angle theta. Here theta. So this is v1 and v2. Then this is delta v, changing velocity. If we take the ratio delta v by v1, and we can write which is also equal to v delta t by r. Okay, so v1 v2 are equal, so we can delta v by v equal to v delta t by r. Yeah, by rearranging these equations you can write delta v, you can write delta v by delta t equal to v square by r. From that you can write the instantaneous acceleration is equal to v square by r. Okay, and we'll come to this equation. Force is mass into acceleration, mv square by r. Force is mv square by r, which is equal to the magnetic field qv cross b. Okay, qv cross b. Then from that mv square by r, we can take mv, momentum, mass into velocity as momentum, mv into v by r. Then substitute here qbr. Then rearranging that equations, you can write the momentum mv equal to qbr. From that you can find the radius of that circular motion. This radius. Okay, the radius of this circular motion. Okay, you can find as R equal to mv by qb. Again you can control the circular motion or the circular path is defined by the mass of the ions, mass of the ions, for which we are finding the mass. Okay, and velocity is again controlled by the magnetic field and electric field. Here the radius also depends on the mass, velocity and qbr, both. Again v is E by b. Then substitute, when you substitute that velocity equation equal to E by b, it becomes, then, and rearranging that equation you can write mass is equal to qr b square by a. Since qb and v are uniquely determined, each different mass m appears at a particular r. Okay, different masses, only you can control the v, you know the value of q, the charge, and you can control the b. If you control these values, you can find only a particular mass particles are hitting only a particular position. A mass m appears at a particular r. So the mass, you can calculate the mass as qr b square e. To determine the masses of one part in 10 power 6, we must know all quantities in this equation. In practice, we could calibrate for one particular mass and then determine all masses by relative measurements. The fixed point on the atomic mass scale is carbon 12C, which is taken to be exactly 12.000000 U atomic mass unit. Okay, to determine the mass of another atom, we change the electric and magnetic field and perform the same experiment, and we find the change of the mass differences. These differences denoted by the delta. Then the mass of this nonane C9H20 and mass of naphthalene C10H8 is calculated with respect to the carbon 12 as 12. Okay, carbon 12 m hydrogen 1H minus mass of carbon 12. Then this the system of measuring small differences between close-lying masses is known as the mass doublet method. Mass doublet method is known as the system of measuring small differences between close-lying masses. It is also possible to determine mass differences by measuring the energies of particles in nuclear reactions. Consider the nuclear reaction X plus X tends to Y plus Y, in which a projectile X is incident on a stationary target X. By measuring the kinetic energies of the reacting particles, we can determine the difference in mass, which is known as the Q value of the reaction. It may also be asked in the final exam. Okay, the Q value, Q equal to mass of X, this is the projectile mass of the target, then the mass of the products, mass of Y minus mass of Y into C square. This is the mass energy equation, delta mc square. For example, consider the reaction 1H plus 14N. The resultant particles are 12N plus 3H. From mass doublet measurements, we know that mass of 1H is equal to doublet measurements. നമ്മൾ കണ്ടെത്തിയിട്ടുണ്ട് എന്ത് M1H equal to 1.007825 U mass of 14N as 14.003074 U, and mass of 3H equal to 3.016049 U. The measured Q value is, by substituting these values, we can find the Q value is minus 22.1355 plus or minus the error 0.0010 precision MeV. We thus deduce the mass of 12N. Mass of 12N is equal to mass of 1H plus mass of 14N minus mass of M3H minus Q by C square, which is equal to 12.018613 plus or minus 0.000001 U. The main contribution to the uncertainty of the reduced mass come from the Q value. The 1H, 3H and 14N masses are known to much greater precision. The nuclide 12N is unstable and decays with a half-life of only 0.01 second, which is far too short to allow its mass to be measured with the mass spectrometer. The nuclear reaction method allows us to determine the masses of unstable nuclides whose masses cannot be measured directly. So, mass spectrometer le kandathan pattathathu nammal endu cheyum adoda energy difference kandittu nammal kandathu. Nucleate abundance. The mass spectrometer also permits us to measure the relative abundances of the various isotopes of an element. Then isotope separation. If we set the mass spectrometer on a single mass and collect for a very long time, we can accumulate a large quantity of a particular isotope, enough to use for laboratory experiments. Some mass spectrometers are designed to process large quantities of materials. Then we will go to the isotope separation. അങ്ങനെ നോക്കാം, laser isotope separation ഉണ്ട്. അത് നമുക്ക് ഈ പിക്ചർ ഡിഫൈൻ ചെയ്യാൻ നമുക്ക് അടുത്ത വീഡിയോയിൽ ഡിസ്കസ് ചെയ്യാം.